Welcome to the presentation of our work, Guess What Moves? Unsupervised Video and Image Segmentation by Anticipating Motion. This work is done in collaboration with Laurynas, Andrea and Christian from the Visual Geometry Group at the University of Oxford. Motion is an important cue for our scene understanding ability. Motion quickly draws our focus to the salient part of the scene. Our mind then naturally associates appearance attributes to the salient component, which helps us identify it under complex motion or heavy occlusion. This learned association between appearance and motion helps us identify the salient object, even in a still frame without any object motion. For unsupervised video segmentation, a task to extract the main objects from a generic video sequence, motion helps to focus on the parts that might be of interest. It also helps in disambiguating between complex visual patterns, in the extreme case, even breaking camouflage. Motion in itself is a very useful cue, such that some of the recent methods propose only using the motion as captured by optical flow, arguing that it is easier to model. We instead take a moderate view and re-emphasize the importance of using both appearance and motion modality. There have been many prior works using both appearance and motion, even in the fully unsupervised regime. Several methods consider motion and appearance in separate pathways. This either requires modeling or even predicting the motion of the objects, which is a difficult task. If the optical flow is used as input, this becomes restrictive in an online setting. For methods that consider only motion, a further issue arises when the object stops moving. We instead propose a single network trained end-to-end. Our method does not need motion input during inference, but can optionally use it. And it can be applied to videos and still images alike. Now we describe the Guess What Moves or GWM model in details. We train our model on video frames. This enables extracting optical flow using off-the-shelf frozen networks such as Raft or unsupervised AR flow. The segmentation network simply segments a single RGB frame into foreground and background. As this is a standard segmentation pipeline, we can use any off-the-shelf segmentation architecture. This is the only learnable module in our model. The component flow model takes as input the predicted masks and reconstructs the input flow F using a quadratic piecewise model with the least squares solution. The network is trained to minimize the residual error between the input flow and the reconstructed flow. The idea is that for the flow patterns to be explained well by the simple quadratic model, the masks should roughly correspond to the independent objects. If the pixels that move together are not grouped together, the component flow model cannot reconstruct the motion of the scene well enough. This model is capable of learning binary segmentation from motion, but in the real-world scenarios, modeling foreground and background motion with one component each leads to suboptimal results. For example, a single component cannot explain the background when there is a parallax effect. Similarly, for complex foreground motion, a single component will have difficulty to explain the motion fully. We hence propose a simple extension of our model to handle this. Instead of performing foreground-background segmentation, we predict multiple segments. We found predicting 4 segments works quite well. The rest of the training method remains unchanged. To combine the multiple segments back to binary segmentation, we propose a novel inference time merging step. During inference, we take dense appearance features from the backbone of the segmentation network and average over the k components separately to obtain the mean appearance feature for each component. This enables us to perform simple spectral clustering on a graph of pairwise similarity between these segments to form the final binary segmentation. Here we show some qualitative and quantitative results on multiple datasets. We perform comparatively to the state-of-the-art methods in the unsupervised video object segmentation benchmarks. Our method works quite well for different categories of objects. Our model is also able to handle scenes where multiple objects are in the foreground. The main advantage of our approach is that we train with a segmentation network that simply looks at RGB frames. Thus, we can apply it to various image segmentation benchmarks and have competitive enough performance, even though it has never observed such instances of birds, mushrooms, and so on. It does occasionally struggle in ambiguous scenes where it is unclear what the focus is, or where you have typically large stationary objects as the main focus. Please visit the project page for the links to the paper, code, and videos. And feel free to reach out with any questions and comments. Thank you for listening.